Welcome to this week 5 lecture of numerical methods and computer programming. Today we'll be discussing about ordinary differential equations and how to solve these ordinary differential equations ODE using numerical methods. That is our main concern today. So therefore we will be stick to only ordinary differential equations and not going to any partial differential equations in this class and within this course as well. We will be learning that ODE is solved by analytically, so that concept, analytic methods which we have done previously, that will be helpful for us in this course as well. Using analytic method, we will be solving some ODE, and after that you will be using different numerical methods which we will be learning today. We will be comparing with the true solution, that is the solution made by the analytical approach, and we'll be comparing that with the numerical solution what we'll be learning today. So therefore, before I go to the methods to solve ordinary differential equations, I need to explain something regarding this ODE. So let's start our class today. First of all, the question arises, why study differential equations? You might have learned this thing what we have taught you in the very first class about the bungee jumper equation. As you can see, it was a differential equation. So dv by dt was equals to g minus cd by m multiplied by v squared, and this was a differential equation. And also, if you see, another equation is provided here for your convenience, which is a very familiar equation, is the motion of a swinging pendulum. The reason why we use differential equations is, in most cases, or in many cases, you will be watching that we can express our physical phenomena in a best way would be the differential equation, or if we use the rate of change of the particular function we are dealing with, it will be easier for us if we express these in terms of that rate of change of that particular function in many cases. So if I give example of this, you can see these two examples what I have provided here. The motion of a swinging pendulum, where it says we can express this with the differential equations, that is, we can use double derivative, or acceleration can be used here in the motion of swinging pendulum. And whereas in bungee jumper equation we can use the differential equation, that is, the change of velocity is known to us. So using that particular phenomena or criteria, we might be going to derive the original function of velocity, or if we say theta for the motion of swing pendulum. So in these cases, you see, we are using ODE. This is the reason, not because just we have learned how to solve ODE in your mathematical courses, what you have done maybe in the previous courses in your undergrad course or program, but today or in this course we are giving some practical examples and why we are using this type of differential equation. That is a very important thing in our course, just because we are not learning anything which will not have any application over our civil engineering. Everything we are learning here, you must have the application you will be getting here in this course. So that's why I say don't miss any portion of your course. Even if you have missed it from the beginning, I will suggest you to review all the videos of our course of GS 4353. It will be very helpful for you, not only in your BSc life but also for your any higher studies or throughout the life, you will be finding it a lot more important for you. Anyway, if I go for the again, if I review this bungee jumper problem and continue the importance of differential equations, I can go to this one where you can see that the physical law says F equals to ma, from which we get or we obtain ODE, that is the ordinary differential equation, that is dv by dt equals to g minus cd by m multiplied by v square. Now if we made analytical approach, we go for this one, which is very tough task for you, obviously, for not only for you but also for almost everyone, just because this is very complex thing which we will be able to get analytical solutions for this type of equation. On the other hand, if we go in numerical techniques, as we all know that this dv by dt is nothing but the slope. And if we assume that, although we think that we can easily understand or predict that this v, the velocity function, will be, obviously this will be a curvature shaped function. It must be. Not in very rare case you will find it that the v velocity will be straight line. But even if we think that although the v, not only the v but also the dv by dt, that is the slope, will be different at different points, it will not be constant throughout the function, and that's why dv by dt will not be linear. But still then, if we assume in numerical approach that okay, this dv by dt is linear throughout the function, then this equation you will be getting. And this is very easy to find out just because we have used just linearized function. If you can easily understand this thing, if you just replace this v with y and this t with x, that is y minus y1 y1 minus y2 divided by x1 minus x2, that is the slope, that is this function equals to this function, and this is nothing but dv by dt. The slope will be y1 minus y2. If I say this is y1 and this is y2, this is x1 and this is x2, then it indicates that we have assumed a linearized slope. This slope is linear, and for this it might be x1 y1, x2 y2. If I assume it like this, then this is nothing but the slope, that is dv by dt. If we say dv by dt is this slope, and for the slope we can use the formula y1 minus y2 x1 minus x2, and this is the slope which will be equals to this one. This is the slope dv by dt, and that's how we can rearrange this equation, rewrite this like this one. So this is the approach of numerical method, where we'll be assuming this as linear function, and as it will not be linear in real scenario, that's why we will have to modify our correction as well. So first of all, the very generalized thing which we'll be learning, that assuming it linear throughout the function, that will be one method, and correction over this method due to some errors, we'll be learning also that particular corrections, some corrections are there which will modify your assumption and take you close to the original solution. That will be also our expectation in this particular class. However, the thing it mentioned here, if you can notice, independent variable are spatial and temporal, and obviously in real life scenario we usually see these two types of independent variable. If you can understand what is spatial, spatial means related to space, that is distance, we can say x, distance. Okay, so this is a variable, independent variable, obviously, which doesn't depend upon any other thing or any other variables. And another thing is the temporal, that is, we can say the time. So time means we can use time different times, as you can see here as well, we are using time. So that's why these two things are independent variable in most cases, either x or t we use in our engineering practice. That is what we mentioned here. However, the two types we usually see in case of ordinary differential equation. Before that, I would like to ask you, what is ordinary differential equation? I know you know that, but if I review this thing, what is ordinary differential equation? ODE is nothing but where the differential equation is only related to one dependent variable. One dependent variable, then we will be calling this as we know ODE. And when there will be multiple dependent variables instead of one, then we'll be calling this as PDE, partial differential equation, as we all know. So ODE there will be only one dependent variable and only one independent variable as well. In case of PDE as well, in each case we will be getting only one independent variable, that's true, but the dependent variable will not be one, you'll see. So that's why ODE, if I say that, let's say that the one dependent variable is y and one independent variable will obviously be there, then that will be x, say. So there will be only equations like y and x, and that's why in ODE we use dy by dx, like this one. Or if it is dv, then dv by dx. Or if the independent variable is t, then we can say dv by dt, as we have shown example in previous slides. And in case of PDE, we usually use del instead of d. So therefore there might be multiple independent dependent variables like dv, dw, or there may be multiple variables like this, and we'll be differentiating this with respect to t, an independent variable. So might be like this one, so 5 plus dw by dt. So this is an example of partial derivative differential equation. Whatever, that is not our concern in this class, but rather we are focusing in ODE, and this ODE might have multiple orders as well. So this one may be like y prime, this is y prime, we can say in ODE. This is dy by dx equals to, if it is 5x, then we can say y prime equals to 5x. And the order, this is the first order derivative equation, as there is only one derivative which we have used. If it is multiple derivative like d2 by dy, d2y by dx2 equals to 5x, say for example this, then we'll be saying this is double derivative. So the order of the ODE is 2. So these things, I hope you know, all of you know these things. The main thing now we'll be going to, that is, let's go back to the slide. There are two types of problems we say in ordinary differential equation. The first thing is where the boundary value problems, we say, where we'll have the values known in the boundary points. Boundary points, we know the values, and the values will be either of y or either of y double prime. Whatever it is, it will be the same thing or the same value, either y. If we say y, then we'll have the values of y only, not the y prime, in all the points or all the boundary points. And in case of initially value problem, in that case, particular case, we'll have the value at only one point, but it might be the y value also y prime value, or multiple, whatever the values are, it must be in at one point, what we say the initial value problem at one point. But in case of boundary value problems, so please forget about this slide. Better if I give example to you, that I think it will be clarified further. Although I think that you know these things, but I'll be trying to make you understand or review this thing to you again, whatever. So if I say for example, I will be giving the example of double derivative in both cases, so that you will find it easier for you. So if in boundary value problems we say, if it is a beam, think about this. This is a beam. This is a beam. Now we want to take the deflection value. Say for example, this is the x value, and deflection is in y-axis, so the deflection value will be y. In different points, the value of y will be varying with the change of x as well. So that is our constant, say for example here. So we in any case, and you will be using this thing as well. You have watched this thing in case of I think you will be watching this thing in case of mechanics of solids, another course which will be I think you have taken this course as well. In the same time, in the same semester, there will be version 2 for you in the next semester, probably for this mechanics of solids. So in this course, you will be finding this deflection value of any beam is related to the distance, this distance of beam from a particular point, from initial point. So in that case, you will be learning that this y value, the differential equation of this y, we use this differential equation of y, or differential equation of moment in many cases, or of load in many cases. So there might be double derivative, triple derivative. Okay, so these derivatives you will be finding there, where higher order derivatives will be used for evaluating deflection, shear force or bending moment, or uniformly distributed load, whatever we say. Different things we might be evaluating this using the differential equations. In those cases, boundary problems are used, like if you know this deflection, say for example, this is y, and this might be deflection, or this might be moment. If we say better if we start from moment, say for example the moment. So what we get from the moment, if you all know that in case of moment, bending moment and shear force, say for example this is the shear force of a beam, and the bending moment is like this one. So from this we understand that the bending moment at any point is the slope of the bending moment at any point is proportional to the value of shear force at that particular point. Say for example, for this one, throughout these points, the bending moment, the slope of the bending moment, you see this is a straight line. That's why the slope of these points are constant, and that's why the shear force value is also constant. So we can say this is proportional to the derivative of what we say. We can say the bending moment, the moment's derivative with respect to x is proportional to, we can say this, the shear force. Okay, or we can say v. Instead of SF, we can say v. This is shear force. And again, you think, if we further make derivative of shear force, if we go back, say this shear force we have obtained from this particular load, or if we give example of, say the bending moment is like this one, the shear force is say like this one, and we have obtained this from UDL, uniformly distributed load. So if it is V, it is M, and if we say this is W, so if you can understand this thing, that the slope of shear force at any point, the slope of shear force at any point, you can see this slope is constant throughout this distance, this x. So the slope of dv by dx is proportional to w, this one. So that's why u is constant and uniformly distributed throughout the beam. So we can also say this is, as we know that v is proportional to dm, so we can say d2m by dx is proportional to what we say dx2 is proportional to this w uniformly distributed. So this is a phenomena where we'll be getting this moment, this m, say for example this is y in our case. So in that case we can say double derivative of what we say, this is double derivative of moment, which is, it will be equals to, if we get a constant terminology here, and this w udl w, this w may be constant value, say 5, or this may be also a variable with respect to x. So this x, like for example instead of the udl, it might be a function like this, that this type of distribution is also possible, where we can represent this one as 5x, say for example the w is equals to 5x Newton per meter. So with the change of x, the w value will also increase. So in that case it might be 5x, or it might be constant value, whatever it is. So we might say this is a function of x, so it is 5x, we can say. So this is a sort of this is the thing what we have mentioned from the very beginning, that this might be y double prime equals to 5x. This is a ODE, as you can see from this example. So in this ODE, how to solve this? While solving this, you will be finding that we have used either boundary values, or we might use the initial values as well. So what is boundary values? That whenever we'll be solving this thing, we might need, if we use boundary values, we'll be getting y values for say this value x equals to 0, y equals to something, say 0, and x equals to this is L length, total length L, or we can say 5 meter, whatever the boundary value x equals to 5, then we know the value of y is also 0, or it may be a different value, say 2 maybe. Okay, so we will be saying that y0 equals to 0, that means this 0 means x equals to 0. So when x equals to 0, y0 equals to 0, and we can say y5, that is when x equals to 5, then this value will be 0, or we can say 2, as we have mentioned here, it might be 2 as well, or any other values there might be. The thing we have used here, that we have used the value of y at different points, and these are the boundary points. We know the boundary conditions here. So we have used boundary conditions to solve this particular equation, as it is the double derivative equation, as you can see from here, double derivative. So we'll be needing at least 2 values from our concept, similar to the system of linear equation, if you can remember here as well, although it is not the same thing, but as you can see there is order of 2, so we must need 2 known values to solve this equation. So it is basically 2 equations. When we see this is an ordinary differential equation of order 2, then we'll need at least 2 known values to solve this. So these 2 values might be y equals to 0 and y equals to 5 at different points. We say this is at different points. So it may be either y0, y5, and also we can use, say, we might use y prime equals to 0 and y prime equals to 5 equals to y prime may be, say, 1, y double prime may be 3. It was possible, and that's why y0 is 0 and y5 is 0. Although it's not possible like that, just because if you derive this thing, it is very less likely that y0 equals to 0 and y prime 0 equals to 1. But still then, just for giving example, I am saying these values we can give that either y at 0 and y at 5, the two boundary values will be given, or we can give y prime at 0, y prime at 5 as well, or we can give say y0 equals to 0 and y prime 5 equals to 3. So in this case as well, we have used different points and different boundary condition. Doesn't matter whether we have used y or y prime or combination of these two, but the thing is that we need two equations, and in that case I will be giving a point, 2 points or multiple points value, that is the boundary condition. That is the fact when we say this is boundary value problem. And there is another problem, I said initial value problem. And in case of initial value problem, and what we'll be learning today and in our course, that how to solve these initial value problems. The initial value problem, we say in cases where we know this is a differential equation ODE y double prime equals to 5x, and we will be using, we know that we need at least two known values. So in that case, for that beam, we will be using any points, this point, this point, this point, and usually we use initial value problem. So initial value means the initial, the starting point of our calculation, that is in this case x might be equals to 0. So that's why this initial value problem means we will be giving the values, the known values at only one point, and that it will be the initial value. And say for example, that's why I will be giving will be needing two known values. So I will be giving y0 equals to 0, and I will be giving y prime 0 equals to 1. Say I have taken this one and I have taken this one. So in this case, you see I have taken the values at just one point, the initial value point value, that is x equals to 0. So y of x when x equals to 0 is 0, y prime when x equals to 0 is 1. So these two values are given for solving this one. Then I will be calling this as initial value problem, that will be giving y prime, whatever it is, but the point value will be only 1 point. Rather than when we'll be using boundary value problems, we'll be giving at different points, the value will be given in different points, and that's why we can give either the combination of y and y prime, both of these two, or only y at different point, or only y prime at different point. This is possible for boundary value problems. So I will be stick to only these initial value problems in our course, where the values will be given to any particular point, and if it is double derivative, we'll be giving y naught and y prime naught, and if it is y triple prime equals to a function or a combination of y double prime, say y prime, 5y prime, 2y double prime, something. So in that case, we'll be needing three known values in initial value problem. So in that case, we'll be giving, say for example, y prime 0, y0, y prime 0, y double prime 0. At different points, we will be giving this sort of known values, so that we can solve three known values using. So this will be also called the initial value problem, just because we have used the values at just one point, all the values, known values. So our main concern today will be initial value problems, and based on which we will be learning some methods or techniques to solve this ordinary differential equation. So let's go back to the slide so that we can move further. Okay. Solving initial value problems. ODE of the form dy by dt equals to function f t y. If the independent variable is t and the dependent variable is y, then this is the format, will be solved using the one-step methods having the general form of yi plus 1 equals to yi plus phi multiplied by h. H is the step size when if you can see this in this figure. If we start from this point, this is the initial value which we know the value of y at this point, and we also know the slope just because dy by dt is the function of ODE, so that we know the function of dy by dt, the value, slope value, and that's why we'll be using this value to predict what will be the value at xi plus 1, and this is the step size h. So if you know that if x is 0 and xi plus 1 is 0.5, then the step size is 0.5. So this is the h, and using phi is the increment function, what we call, and it is used to extrapolate from an old value yi to a new value yi plus 1. So this yi plus 1 will be predicted, although it will not be just above the function. We know just because this is an assumption, there will be error generating from this, but whatever it is, this is the prediction for solving the ODE. So this one will be our increment function, and extrapolate means to what we know this is anticipating. Extrapolate mean is to anticipating, whereas in interpolation we have said interpolation problem, if you can remember that we knew the values of 2 points or 3 points, and we have fitted this in different methods, either graphically or Newton's polynomial or Lagrange's method, and we would like to get or find out values, intermediate point values, not outside these data. We were very much confined to the values which were within the data points, not outside of the data point. So in case of this one, we say extrapolate just because we are extrapolating, we are going beyond this point. This is not a cordoned area, so that we will be getting the values within that. So from this point, we'll be predicting, we'll be taking the next value, which is extrapolation, we say. Okay. The techniques might be the techniques which will be we using in initial value problems are Euler method or Euler techniques, Heun's method, midpoint method, and Ranga Kutta method. As you can see, the fourth order Ranga Kutta is very much popular among people, which we can use for solving initial value problems as well. So let's see the first one, the Euler method for solving any ordinary differential equation. So this is Euler's method, where we are predicting the very linearized slope, although it might not be the linearized slope. The first derivative provides a direct estimate of the slope at ti, slope ti, the first derivative, dy by dt at ti is equals to f of ti yi. So we are assuming this is a function like f t comma y, which is equals to dy by dt. The function will be given to us. Now Euler method uses that estimate as the increment function. The increment function, we have taught that yi plus 1 will be equals to yi plus this phi increment function multiplied by s. And what will be this increment function? In case of Euler method, it says the increment function will be the slope. Slope at what? Slope at the point of I. To predict y value at point yi plus 1, xi plus 1, that is what we have given, or ti plus 1, and for that we'll be using this one, which is known to us, the initial value this is, and plus h is the increment, which will step size, which will be using. The increment function says to predict yi plus 1, we will be using the slope of we will be using the slope at the point this one, ti comma yi. That is the slope at yi will be used here to predict this one. So if we focus on the figure, which will be understanding this thing very easily. If we focus on this particular figure, you see dy by dt is given. What is dy by dt? dy by dt is the slope at the function. So if we know the function slope, that means we know the slope. So the slope at this point is known. This is the slope, and slope of this point is known. Okay. So we don't know the function. Remember one thing, the original function we don't know, but we know the slope at different point of that function. Which function? We don't know that function, but we know what, say this one is a function, but we don't know what is this function. This function of x, what is this function of x? We don't know. It might be x squared plus something 5x or dot dot dot, but we don't know this function. But rather that we know f prime x, or we can say y prime. We know function of the slope at different points. So that might be a function which is indicating different point slope by this function. So we know slope at different point of that function, but we need to evaluate that function. That is the solving of ODE, and for that we are using slope at this point to predict the function value at this point, and this is yi plus 1. We say this yi plus 1 means the function value at yi plus 1. So if I further make it clarify to you, then I'm going to script so that it will be easier for you to understand. Say for example, this is the function. This is the original function, not the ODE function. This is the original function, but we know slope at different point, that is the derivative function. So this is y, but we know y prime, or dy by dx we know, that is slope at different point as known, but the initial value is also known of the function. That is, say for example, this point is y naught, although it is not y naught. This is y naught, means x equals to 0 if then y value at 0 is known. Say for example, this value is 3. This value is known. The function value at x equals to 0 is known, but the function is not known. What is the function? This function is not known, but the function value at x equals to 0, or initial value, is known. And what we know? We know the function of y prime, that is dy by dx. So we can exactly evaluate the slope at different points, at this point, at this point, at this point, just because we know the original function of dy by dx. So slope at different points we can easily calculate. So that's why what we are doing, we know this particular point value. This y naught is known. Say this is 3 is known. We are using this one. Say we will be trying to calculate at x equals to 1 what will be the value of y1 equals to what. That is our concern. This value we don't know, but we will be predicting this value. What will be the value? Euler method says, although we can see from this that the slope, you can understand there, the slope is changing at different points. Slope is changing. So the slope at this point and slope at this point is not the same. But the Euler method says we'll be assuming the slope as same, and that's how we'll be predicting the next point. So if I redraw this thing here, Euler method says, you know this point, this y0 equals to 3, you know this point, and you know the slope of this point. You will be using this slope value if it is x equals to 0, just for example, and this is x equals to 1. That means step size is 1. This step size, it might be 0.5. If I use 0.5, then it will be 0.5, the step size. So for example, I am using 1. Then what will be the value of y1? Euler method says, as you know this slope, you will be extrapolating this slope at point x equals to 1, and what you will be getting here at x equals to 1, this is your result. That will be your y of 1 equals to this value. Say this value, the original value will be 4, but you are getting the value equals to 5. So this is the discrepancy. This is Euler method solution, what we are getting from here, that is 5, but true y equals to t means true equals to 4. So this is the discrepancy. Using Euler method, as we are assuming the slope remains constant throughout the function, that's why we are getting the y1 equals to 5 using Euler method, whereas the true solution says that this will be equals to 4. So that is the Euler method's assumption, linearizing the slope throughout the function. So that is how we'll be approaching in case of Euler method and what we have tried to describe here. And for that, if you use the same thing, so how we will be calculating this thing? This yi plus 1 equals to yi plus ftiyyi into h. This is the thing I am now going to make you understand about. So this value, how we'll be getting this thing, watch carefully. If it is yi, and this will be yi plus 1, which I am predicting, that will be this yi plus 1 will be equals to yi plus this yi, this is yi, this yi 3 plus this portion, and this portion is nothing but, as we know the slope is ftiyyi. This is the function what we have said, that dy by dt, forget about x if it is t, or if I say this is x, whatever, if it is dy by dt equals to, we have said this is the function we say ftiyyi, that is the slope function multiplied by, that is the slope. As we know the slope function, so we can easily calculate the value of slope at point tiyyi, that means x0 and y0 is 3, so we can say f0 comma 3 in this case, that is the slope value at this point, this slope value if we know it, and using this slope value and the step size, say for example this is 1 step size, so using this slope size multiplied by this slope value, this is the increment. This increment indicates nothing but this increment with this yi. So this will be our Euler method assumption, as you can see from the slide as well. So this is yi plus ftiyyi multiplied by h, and this is the prediction, as you can see from our slide, this figure. This is the predicted value using Euler method, and this is the true value, and this difference is called the error generated by the Euler method. And now I would like to say something about the errors in ODE. As you can see from here, that errors are in ODE, the numerical solution of ODE involves two types of error, the truncation error and the round-off error. And you know about these two errors by this time. Truncation error is caused by the nature of the techniques employed, and round-off errors are caused by the limited numbers of significant digits that can be retained and what we are using. The total or global truncation error can be further split into two. If we focus on the truncation error, this truncation error is generated from, if we don't use the higher order, that is, if we say we are assuming this as a straight line, although this is not straight line, the function is changing throughout the points. That's why this slope which we have used, this should not be the linearized slope, rather this one is a changed slope. So if you can somehow predict the nature of the slope so that you can easily trace it, so it is something like a series of a function which we should have used here, but instead of that we have truncated the higher orders and we have stick to the linearized function, and that's why the errors generated by truncation error. And this truncation error can be further split into two portions. One is the local truncation error that results from an application method in the question over a single step. For a particular step, if we use the true value and predict the next value for that particular step, the error what will be generated, that will be called the local truncation error. And the propagated truncation error is that the results from the approximation produced during previous steps. So these two are the truncation error or global truncation errors we can say, and propagated truncation error or global truncation error, whatever it is, we'll be explaining this thing, I hope, when I will be giving example of a math, then we'll be understanding this thing further. Okay, error analysis in Euler's method. The local truncation error for Euler method is OH2 and the proportional to derivative of fty, while the global truncation error is OH. I think we don't need to focus on these things. Rather, this is an approximation, as we have also elaborated something that in the previous classes or lectures, as you can, if you can remember that in bisection method or in Newton-Raphson method, error can be approximated using the previous error or previous any other function. So this is the similar thing which we have provided here, but I don't think you will have to give a focus on this thing. This is not required for our mathematical problem solving. Rather, focus on this figure. This is the true solution. So whenever you will be increasing step size, or you are using h equals to 0.25, less amount of step size will give you less amount of deviation from the true solution. But if you use larger step size, then it will take you far away from the true solution. So as much as the step size will be increased, the error will be increased. And if you can decrease the step size, your true solution, it will be close to the true solution using Euler method. But if you see here, this is even if we use h equals to 0.25, the error seems very significant here. So that's why Euler method is not very much significant, but still then the significance of Euler method was this, due to this method, as the generalized assumption was made here, that's why we can modify this further. And what the mathematicians have done, that they have modified this Euler method to get close to the original solution, which we'll be discussing later on after one example of using Euler method to solve any ODE is shown. However, global error can be reduced by decreasing the step size. This global error, what we say that global error is once this initial value is known, y0 equals to some value, say 1 is known here. Once you go the predicted value of this one, but you don't know the true value, and the next step you are using this value for predicting this one, just because you know the slope at this value, and the same thing you have applied in this point, just because you don't know, you have not used the true value, rather you have used this value what you have obtained for using Euler method. So that's why this error is a global error, that is one by one you are taking this assumed value, rather not going back to the true value, just because we don't know the true value at this point, this point, when we are using numerical methods. Analytical solution is different case, what we have shown in this figure, but in real case, when you are just propagating your assumption, your Euler method throughout the numerical techniques within the problem, then your approach will be like this one, and you will be taking the slope of this slope within this point, then go to this one, then you will be using slope at this point as this one, just because you know the slope value at each point. but you don't know the function. So you will be going to this one, then the slope value is known in this point like this, so you go to this one, but this will be generating the global error. But the local error means if you all the time you come to the original true point and use the assumption of this slope and go to this point, instead of using from this one you go to this point. So this will be raising the global error, what I am saying, global error. But if you use true value in each step to predict the next point, then the generated error, this point, this error will be called the local error. That is the error at this particular state, that will be called the local error. So we'll be learning or this thing, how to solve, how to calculate with an example what I have provided here. So this is the problem. As you can see, it says use Euler method to solve to numerically integrate this function dy by dx equals to minus 2x cubed plus 12x square minus 20x plus 8.5 from x equals to 0 to x equals to 4 with a step size of 0.5. That is, I will be starting from x equals to 0, then I will be predicting x equals to 0.5, then I will be predicting x equals to 1, from 0.5 to 1 increment of 0.5, then 1.5, then 2, then 2.5, then 3, then 3.5, then 4. So use this thing to numerically integrate this function. This is the slope, we know. The initial condition x equals to 0 is y equals to 1. That is, we know the value of function at x equals to 0, this y function, but not this function. This is called the slope function, but this is the original function, but we don't know the original function, but we know the value of original function at x equals to 0 only. So we'll be using this one to predict using Euler method all the other points from x equals to 0 to x equals to 4, and we'll be recalling that the exact solution is given by this equation. This equation is given, so find true error for each step. So it doesn't ask for for any particular error, global or local, it defined, then you will have to find out both errors, global and local, both errors for each step. But if it says find local true error for each step, then you will be only finding local true error. If it says find global true error for each step, then you will be finding only global true error. Unless it is specified, then you will be determining both local and global error for each step. So there is another thing, the exact solution is given by the equation. This solution might not be given as well. What will happen if I don't give the exact solution? I can also get this one by solving it analytically. What we can do, I can integrate this function, then one constant will be arisen here, and as we know x equals to 0, y equals to 1, I can put the values here to get the constant, and I can easily get this function. So you can recheck it whether you get this value or not. So in your exam, this function exact solution might not be given as well. In that case, you will have to solve this analytically first, just because you need to find the true error, and for true error you need true value as well, in line with the Euler's method solution. So let's start this problem. Let's solve this thing. I will be now importing the question here. I'll be importing the question. This is the question for us. So we can say this is dy by dx, and it is equals to function of x comma y. I can say that is the function of slope. what we need to calculate is, first we will be going for, using Euler method, we will be predicting y.5. If you can remember, yi plus 1 was yi plus this increment function, which is fx comma y multiplied by h, that multiplied by h. So this will be equals to initial point known, that is y0, plus the increment function fx comma y multiplied by 0.5. So instead of this one, I can say if x comma y, this is, rather we say x here is 0 and y here is at x equals to 0, y1, so we can say y0 is 1, so this 1, and this value is, we put this value in this point, so this we can say f0 comma 1. Okay, remember, in the first step, very first step, we are using the true values, but for the next steps, for local errors we'll be using true values. For global errors, we'll be using the values we'll be obtaining from using this Euler method solution. Okay, what is the value of this slope at this point? So the slope at this point, where x equals to 0 and y equals to 1, as there is no y in this particular function, so we don't need this, but if there were any other point or function, the function includes this y, then you will have to put y equals to 1. So as there is no y value here, you can see, so we only put the value of x here. We'll be getting dy by dx equals to 8.5. so that's why we can say f0 comma 1 equals to 8.5 in our case. So that's why this will become 1 plus 8.5 multiplied by 0.5 according to Euler method, and this will give us the value of 5.25 at y equals to 0.5. X equals to 0.5, the value of y will be 5.25. Whereas the true value, we can use the true solution. The true solution, as you know this function, so put the value of x and y, x equals to 0, y equals to 1 at this point, sorry, x equals to 0.5 at this particular analytic solution. In analytical solution, we all know that y equals to a function of x. This is the format of analytic solution. So no y is required in this portion. So only x will be enough. And that's why this 0.5, we can put this value here. True solution, we can say true solution of 0.5, and we can say this is Euler solution at 0.5. So true solution at 0.5, put the value 0.5 in case of x here, you'll be getting the value as 3.21875, if I'm not wrong. So now in the first case, very first case, as we have used the true value, and we will be using true value, no initial Euler assumption value in the first step. So in first case, the percent global error, true error, will be equals to percent local true error, which is equals to, as we know, the true value minus the predicted value divided by the true value multiplied by 100%, and this is 63.1% is our error. You think about it, we are using Euler method, linearized slope throughout the function, constant slope. So however, using these two values, ye 0.5, we have obtained 5.25, and y true value was 3.21875. Using these two, you will be going to the next step. So if we are here to find the global error, sorry, the local error, next step. Now I'm calculating x equals to, this is the next step, means I am using x equals to 1 using x equals to 0.5. The previous step was x equals to 0.5, we are determining from using x equals to 0. That is y0 we have used to get y 0.5. So in case if we are first for going for local error, calculating local error, then what we'll do, in local error we'll be taking yt. That means the true value is taken, only the error generated from this particular step will be calculated, that is local error. And the global error, the error will be retained from obtained from the previous calculation, that is we'll be using this value to predict the next one. Then the total error will be obtained here, that will be called global error, but local error will be taking yt. Okay, the similar thing now we'll be using y1 will be obtained using the previous value y 0.5 plus f at 0.5, and we don't know this value yet, we know this value, sorry, and we'll be using true value of 0.5 in this case. So this y t 0.5 is here, or we can say y t 0.5 is this one, so 3.21875 multiplied by 0.5, the step size h. Now we don't know this value, this slope value. Now we'll have to calculate this slope value, and remember one thing, this slope value is always the true slope, just because we know slope, exact slope at each point, just because this function is given, this is the slope, fxy is known. So we'll be putting the value of this 0.5 and 3.21875, although there is no, as there is no y in this function, so only x equals to the 0.5 value will be putting in this equation and obtaining this f.5 yt 0.5. So this is equals to, basically this is the dy by dx, where x are there, we'll be putting the value of x equals to 0.5 in that equation, this is the equation, and you will be getting the value. I'll be calculating this one, although this 3.21875 is of no use in our particular this math problem, but in any math problem you have y included in dy by ds function, then you will have to use this y as well. Remember this thing. Okay, this value will be obtaining as 1.25. So let's use this, y1 will be equals to 3.21875 plus this one 1.25 multiplied by 0.5, and this is also prediction, no doubt, using Euler method, but not the Euler method we are expecting universally. So don't we don't write anything over there, just y1 here will be 3.84375. okay, so from this the true solution can also be obtained from the analytic solution. So we put x equals to 0.5 in this function, which will give us y equals to exact solution will be 3. So now as this is local error, we have taken y true value, so the percent local true error will be equals to the true value minus this one divided by 3 into 100%, which will give us minus 28.125%. That is the error generated solely from this particular state. But if we want to calculate the global error, global error, so I will be taking Euler value obtained from the previous state, that is this one, therefore, and we will be denoting it as y Euler 1, although we haven't represented anything here or here. This was just for local error, but the original Euler method indicates this value, which we'll be getting from Euler, taking Euler, that is the next Euler value. Y Euler 0.5. Now we are using Euler value instead of true value. 0.5 comma, this will be Euler value as well. So the Euler value was 5.25 multiplied by 0.5. This will be equals to the Euler value 5.25 plus this one will have to calculate from, put this 0.5 and 5.25 in this particular function. As there is no y here in this function, so x equals to 0.5 will give the similar result to this one, this one, just because this 5.25 or 3.218 is will be giving no impact upon this function, just because only x is there. But if it were any y in the function, then this value 1.25 might vary with this one as well. But in our case, in this particular case, this will be the similar thing. But remember this thing while you are calculating for your problem, whether there is any y or not. So you will have to again calculate for this function if you find any y there is in the differential equation. However, y Euler, the next value we'll be obtaining from this will be 5.875, and the true value again in this case, true value of 1, we can say this is true. This one was actually true value of 1 was 3, and true is always true, so this is 3. So if I find percent global epsilon t, that will be the true value obtained, that is 3, minus the Euler value obtained using Euler value, that is this one. So 5.875 divided by 3 multiplied by 100%, that will give you a value of 95.83%. Think about it. This is the global error, that is propagated error using the error generated in this one and error generated in this particular arc. These two will give result to this one. As a whole, global error is this one, and the local error means this local error indicates this local epsilon t indicates only the error made by this particular step, not the previous step error is propagated, as we have taken yt true value at the beginning of this step. But as we have used the erroneous value of Euler which we have obtained from the previous step, and that value is used here, that's why it gives rise to the global error, as you can see. So that's why this will be called ye all the time. So in the next case, the next step, similarly we'll be calculating x equals to 0.5, that is y when 1.5 when we know y at 1. And in that case, if you use true value here, then you will be getting local error, and if you use Euler 1 here, then you will be getting Euler value for the next step. And these values are ye is 5.875, or either you can use yt, that is the true value. You can use what we have obtained, this one, for the next one. So if you use this yt for calculating y at 1.5, I will not write anything here. If you use t, that will give you local error. So you will be using yt at 1 here plus dot dot, you will be getting local error. And whenever you are getting Euler, using Euler value, then I will be writing ye, that is the original Euler value. It will give rise to global error, no doubt. So you'll be using this one here. So that's how you'll have to approach. And I'm not going for the further steps, rather I am writing down the solution here as a whole, so that you will be performing this in your home, and you will be checking this with this value. This is y Euler value x, y true, y Euler, and this is the error. We can write this is the error, percent relative error, and for that two division, either global or either local one. So we can divide it like this. So I am now writing down one by one. X equals to 0, x equals to 0.5, x equals to 1, x equals to 1.5, x equals to 2. If I go further, 2.5, 3, 3.5, and finally 4. In exam, I might not be giving you all these things. I might give at least 1 or 2 steps or 3 steps for you in the exam, but this is for your practice so that you find the values correctly. So for y equals to x equals to 0, true value was always the same. The first initial beginning, there was no Euler value there. Sorry, not 2, this value was actually 1. As we have started at the very beginning, the value was 1 for x equals to 0. So we can write y true 1, Euler was also 1 in the very first case. And in the very first case, the global and no local error was there, just starting. But for 0.5, the starting, this step indicates the first step we have done here. This step, first step. In this case, true solution of 0.5 is 3.21875. So 21875, and the Euler value we obtained was 5.25. And this is minus 63.1 we have obtained, and both local and global error was same, but when it was 1, the true value we obtained 3. True value we obtained 3 using analytical solution. So this was 3, whereas the Euler value we obtained here was 5.875. Don't be confused. Again, I am saying you might be making mistake in your exam as well. Don't take this value as Euler value. This is just for calculating local error. The original Euler value will be this one when you will be taking the Euler value from the previous steps. So 5.875 will be the value. 95.83% global error and local error was 28.125. Now I am just writing down all the values. 2.21875 to 2.71875, it will be 4. 4.71875, it will be 3. And it is 5.125, 4.5, 4.75, 5.875, 7.125, 7. It will be 131%. And this will be 125, 74.5, 7, 46.9, it might be minus 51, minus 133.3, and the local error will be minus 1.41, 20.5, 17.3, 4 minus 11.3, minus 53. So these are the values. You will have to check it of your own. Now I'm going back to the slide. So now we see that this Euler method is very much erroneous. That's why we need to improve this Euler's method. The main limitation is the derivative at the beginning of the interval is assumed to apply across the entire interval. So we are using this one throughout this total interval. I am taking this slope, although the slope is changing. So I need to change my prediction. I cannot go like this one. This slope cannot be used, or the slope of this point cannot be used throughout this step h. So this interval h. So that's why two modifications can be made. One is called the Heun's method and another is called the midpoint method. So first of all, I'm going for the Heun's method, which we also call the predictor corrector approach. What does it say? This says the prediction, what we have predicted, this prediction should be corrected. That's why we say this predictor should be corrected. We cannot use this slope, this like slope. Rather, I'll have to change my prediction so that it gets close to this true value. And this correction is obtained using the slope of this one and this one, average of these two slopes can be taken. You see here, slope at this point is like this one, slope at this point, we know slope at each point, you know, so slope at this point, all are known. So slope at this point is this one, as it is shown here, this one, and slope at this point is this one. So what we can do, the slope at this point and slope at this point can be made average, and in between these two, the slope, the middle slope, can be approached like this one. So what we will be doing, we will be taking slope at this point and slope at this point, we will be making average of these two slope, and the average slope will be applied in this point so that we can get close to this point. So you can see here the slope is taken f t I y I plus f t I plus 1 comma y not I have said I plus 1 divided by 2. So this one is the average slope which will be applying in this point, and this slope is nothing but the increment function. That is, predictor was first initially, the predictor will be this was the increment function. Now I will be correcting my prediction using this average value of these two slopes, and the same, all other things will be similar. Just forget about this thing, I'm not going to discuss this, and this will not be required, I hope. This corrector is called the Heun's method, and that is the iteration what we can use for computer programming. So you will be easily understand this thing once you are acquainted with the method. So if you see here in this particular figure, this is the true solution. When we have applied Euler method, this was the predicted solution. But when we have used Heun's method, the predictor corrector approach, you see the solution. The assumption is very close to the true solution. And that's why this is called the modification of our Euler method, which we can use to solve our ordinary differential equations using numerical technique. And now I'm going to show you one example problem to how to solve this using Heun's method. You see this problem? So let's take this one to the script, copy this to the script. This is the question. I will be solving this using the Heun's method. Before going to solution, I would like to say that I would like to suggest you in your exam or for this particular course will be exceptional to all other courses. That's why I would like to suggest that you better use 2 calculators in this exam, because when if I give example of bisection method even or second method thing, you think about we need 2 functions. If you can remember, fxr we need to calculate, or another function was this is the predicted value, and this is the original value. 2 values. One is the predicted value will be calculated using upper limit and fxu fxl. Combination of these two will be used as a function to predict this one, and you might need to calculate fxu or fxl all the time. That is original function. There is an original function like this, so which will be you will be calculating. These 2 things you have to calculate at the same time. So you will have to create a function in your calculator, and most of the time sometimes we see that it will take long time to calculate, and that's why it will be better. And even if it takes less time, whenever you will be going back to this function, once this function is done, then you will have to go back again to this function then what will have to do, you'll have to go back, and that will again take time. And in this exam particularly, you will be getting very less amount of time to complete this all the math problems. And that's why very single lapse of time is very much important for you. And that's why I will be suggesting you to take different calculators and create different functions. You give input to this function for one value and run this one for another, so that you will not have to go back or get back to this function after this function within one calculator all the time. That will save your time. Yeah, this is just suggestion. You can use one calculator as well as you are using. That doesn't matter. I'm just giving this example. So for this is from my experience from our course. Whenever we have given exam for this one in BUET, we used to use two calculators, some of the students, and some are very meritorious and they were very much balanced in time, so that they might have used one calculator as well. But for me, I was stick to two calculators just because this was very convenient to me. And even if I give example of the admission test, even whenever I've given admission tests in BUET, say there were different questions. There are MCQ as well. There was written. In MCQ questions, there might be, you know, that very limited amount of time is there. MCQ question, there might be a question like something function ex, ln x, something like this, dx, 2 to 4. What will be the answer? There are 4 multiple choice questions. So what I used to do that. Why are we going for the analytical solution for this? That doesn't matter. This is an MCQ question, so better put this value in the calculator. As we have function in ES calculator, we had the option for numerically integrating this value. So we better plot this function, give input to the calculator. The calculator will be giving you output. But what happened that this calculator, the ES, even it was ES calculator, it would take long amount, much time to give the solution. So it was running all the time, say for at least 30 seconds it might take. So in that time, what I would do that, I will be taking my another calculator and I will perform then another task, and I'm going for the another mathematical problem and another MCQ problem in that time. So better when in that meantime I am getting the answer of this one, I have plotted another function, or I have solved for the calculation using the calculator. I have solved another MCQ question. So by that time I have used 1 or 2 more questions, I am getting the result of this one, and I am again giving tick marks to the original result. So that saves time a lot. But if you use one calculator in the time when either you are analytically solving it or using calculator to solve it, you might not get enough time, and you cannot do anything within that particular time. That's why I used to use 2 calculators at the same time. That is also helpful for admission test, also helpful for this particular course, the numerical methods as well. But you will have to maintain your time, you will have to balance your time in this particular course. So I will suggest you to practice these things a lot in your home, so that whenever you'll be giving exam, I will not be with you whenever you'll be giving the exam, but it will help you a lot if you can manage your time using calculators, or even all the steps you should memorize. You should practice so much that, so that whenever you'll conduct your exam, you'll be writing, trying to solve the problems. You will not have to check it from your script again, or your note again whenever you'll be giving the exam. So just because if you even go for the your notebook to see the formula what you have used, and on what will be the next step, then that will also cost you time. So you cannot properly answer all the question in your exam, hopefully. So that's why I would like to suggest you to manage your time in this particular exam, and better if you can use 2 calculators at a time as well. That will be helpful, I hope. Okay, now I will be solving this particular math. So while using Heun's method, I'll be numerically integrating this thing. And what is the Heun's method approach? Before I go to the Heun's method approach, as we'll have to calculate the true error as well, if the true solution, analytical solution, is not given, as we have seen for the previous example for the Euler's method, now I'll have to analytically solve this thing. So first of all, analytic solution we'll have to go for. So analytic solution. Now I need the concept of the mathematical course. Y prime equals to 4 e to the power 0.8 x minus 0.5 y. Now this is an ODE. Now what we'll have to focus, whether it is separable or non-separable. I hope this is separable, and you know this is separable, so we can rewrite this all y in one side and x in one side. Now what we will do, now what we'll try to do is, this is actually this one 0.5 y. Now I'll have to multiply it with a integrating factor. And what will be the integrating factor? From your concept of the math, you know the integrating factor will be here is e to the power 0.5, this 0.5 dx, that is e to the power 0.5x will be the integrating factor, which will be multiplying in both sides. So this will become, after multiplying, it will become e to the power 0.5x dy by dx plus 0.5 y e to the power 0.5x, and this will become 4 e to the power 1.3x. So this one, these two functions can be converged together to get this value. From this we can write, if we integrate in both sides, you'll be getting 0.5x 4 e to the power 1.3x plus a constant term here. Now we know the initial value when x equals to 0, y equals to 2, so we can put the values here. 2 e to the power 0.5x equals to 4, x means 0, 4 e to the power 1.3 multiplied by 0 plus c. So we see from here this will be 2 plus sorry, I have made a mistake. When you'll be integrating this thing, I'll be getting this divided by 1.3, as we know. This divided by 1.3. So whenever I put these values, initial value, this is equals to 4 by 1.3 plus c. So therefore c will be equals to 2 minus 4 by 1.3, I can write. So that function will be y e to the power 0.5x will equals to 4 by 1.3 e to the power 1.3x plus 2 minus 4 by 1.3. Why I'm keeping it like this? Just because I can combine this together. This is up to you, just because this is an analytical solution. You can make as short as possible. 1.3 e to the power 1.3x minus 1 plus 2. So if we want to know what is the value of y only, then I will take this to this side. Then it will become as it will be subtracted from the power, then it will become 0.8x, and it will become minus 0.5x, as it is used here as division, also here as well. However, this is the analytical solution for getting the true values. Now I am going for the our case. I am going for Heun's method here, or predictor corrector approach. The first thing we need to know that the slope at the different points, and we know this slope, and I need to know the slope at this point, but I cannot know this point. Rather, I can go to at best this point. So what I can do, I will be predicting using Euler value. This point I will be predicting, then the slope will be similar to this one. This slope will be similar to this one, but I need to go to this point first. This is yi plus 1, and this is not yi plus 1 in Heun's method. This is yi plus 1 using Euler's method. So better we give y not I plus 1, which is not actual I plus 1 using Heun's method. It is using Euler's method. So I'll go to this point first. I know the x I plus 1, and using xi plus 1 yi plus 1 function, as we know, xi yi. So if we use xi plus 1 comma yi plus 1, this is our slope, and this is the slope at this point, and this is the slope at this point. So these two slopes will be combined and divided by 2 to get the average slope, this one and this one. So this one means this is the intermediate slope, average of these two, and this average slope will be used to predict this point, which will be getting close to the original solution. Okay, so first thing is to obtain y not I plus 1, that is using Euler method. So while performing Heun's method, I must need to perform the Euler method as well. So according to Euler method, y not I plus 1 will be yi plus f xi yi multiplied by h. Now here the step size h is 1. Therefore, and we know y0 equals to 2, the initial value is known. Now we'll be calculating. So therefore, if this one we try to calculate, we'll be getting xi yi, means for our case, if you want to calculate y naught 1, as our step size h is 1, I am starting from x equals to 0. The next step will be 1, x equals to 1 will be equals to y 0, which is known, plus f of 0 comma y equals to 2 at that point, so 2 multiplied by 1. Now I need to calculate this one, f 0 comma 2. So it will be getting this from our function, this provided function. This is fx x comma y. So put the value of y, x and y in this equation. Remember, now recall in your mind, in the previous example there was no y in this particular side, but in this particular math you see there is a y term here. So y is also required to predict y prime in this equation. So put the value of x and y, that is 0 comma 2 in this equation. So you will be getting f 0 comma 2 will become 3. Therefore 2 plus 3 multiplied by 1, that is equals to 5. This is our next, this is the Euler's prediction, not the actual prediction. I am just determining this thing to get the slope value at the point 1. So now I need to calculate slope at this point, and slope at this point can be obtained using this value. So where xi plus 1 is known, that is 1, and y not I plus 1 I have obtained as 5 here. So this one will be calculated now. X f1 comma 5 will be equals to 1 comma 5. That means put x equals to 1, y equals to 5, and you will get 6.402164. This is the next prediction. This was the initial prediction. Now I will be taking average of these two, this one and this one, and use this average value as the incremental function of this one. So that will give you the Heun's method prediction for the next step. So that's why I'm writing here y1, and I'm writing Heun's method h here will be equals to y0 plus the average of these two, the slope at the first point, at the last point. So 3 plus 6.402164 divided by 2. This is the increment function in this case, multiplied by the step size 1. And this y naught will be using 2, as we know. So the value of Heun's method here, it will give 6.7010819. And the true solution, we can also obtain true solution from our analytical approach. Y true solution at 1, if we put the value of 1, x equals to 1 in this equation, this is the analytical solution. X equals to 1, put this value here, then you will be getting the value of y. The true value of y will be 6.1946314. Look here, this is the Heun's method prediction, which is very close to the true solution, and that is the efficiency of this modified approach to the Euler's method. Now I will be calculating epsilon t, which is this true value minus this one divided by 2 multiplied by 100. So I am not writing this, rather I am just directly writing the answer. So in the first this step, both local and global error will be similar. Now for the next step, go to the next step. If you are asked to use the if you are asked to determine the local error, then what you will have to do, you will have to take the true value again, this true value again, for the next step at y, as y equals to y1, as y1. And in case you are trying to global error, and this is the error what we generally use, this error will have to use the value obtained from Heun's method for the next step. So if you use this one, you will get local error for the next step. If you use this one, you will get the global error for the next step, and using this one, what you will be getting, that will be called YH. If you use this one, you are only getting the local error, but what you are getting as Y2, that is not H if you use true. And if you use this one, that will be actually YH2, and that will be propagated further. However, let's go to the next step. Now we know y1 equals to 6 point, the Heun's method result, that is 1.07010819, and we'll be using this one. I am not going for the local error here. So if you are asked to determine local error, then we will have to use true value. And in generally for global error, I am focusing here, and I will not be calculating local errors in this particular math. So I will be by epsilon t, I will be indicating global error here in general in this particular math. Okay, so now for predicting Heun's method at 2, the next point at the step size is 1, I'll have to use YH of 1 plus, the average value I will have to take. So xi yi plus f xi plus 1 comma y naught, that is using Euler method. This value will be getting, then the slope will be obtained totally divided by 2 multiplied by h. This will be our approach here. So this one means already existing point, that is at 1. So this one will be f1 comma this yi means the value we have obtained using Heun's method will be using, that is yh1 will be there, yh1, as we are using global error. For local error you might have used yt1 in this case, but now I am not. So whatever, this will be the value. So let's calculate this one. Y1 comma 6 point, that is yh1 7010819 will be, this is the function. Let's put the value of x and y in this particular equation, so that you will be getting 5.551623, and we need to calculate now y naught 2 first, that is for this one y naught 2 I will have to calculate first, and this is 2. So y naught 2 will be equals to, using Euler method I will have to use 1, and 1 of what? True value or Euler or Heun's value or Euler value? What? In this case we will be again using here the Heun's value, that is this one. So very much careful while writing. If it is y naught 2 for Euler value, I will be using YH, just because I will be using YH as it is global error we are determining. So if you use local error, if we are to determine local error, we would have used true value of 1 here as well. But now what we are using Heun's value. So now I will be writing this one plus this function value, by this time, this value, function of 1,67010,819, which you have already obtained, multiplied by 1. So this is also using Heun's value. So if it were local error, then we might have used true value here. So this one will be equals to 7010819 plus 5.551623 multiplied by 1, which will give you the result as 12.252705. So now I have obtained this point, and now I'll have to determine the slope at this point. As it is known, this is 2. So f of 2 comma 12.252705 is equals to, using the function, this function, I'll be getting 13.68578. This is the slope and this is another slope. So I will be taking the average of these two in this case and to predict the Heun's value at 2. So therefore YH2 will be YH1, that is 6.7010819, plus average of these two, that is 5.551623 plus 13.68578 divided by 2 multiplied by 1, and this will give you the result as 16.31978. 31978. This is the Heun's value for 2. And if we calculate the true value at 2 using the analytical solution what we have derived, this one, then x value, if we put the value of x equals to 2, then we will be getting the true solution as 14.8439219. So we are getting close to the solution using Heun's method, whereas Euler method used to deviate in huge manner. So therefore ET, if we calculate, it will become this true value minus this one by true value into 100%, it will become 9.94% of error, and I am indicating global error here. So now in similar manner you can make approach for the next steps as well. I'm not going to show this, rather I will be giving an outline of the result here. I'm drawing the table. This is x, this is y true, this is y using Heun's method, and this is ET percentage. So let's write down the results. When it was 0, the true value was 2, the initial value was 2 all the time, and when we go in for the first step, we have found the true value as 1946314, whereas the Heun's value we obtained was 7010819, and it was 8.18%. And in the next step, the true value was 14.8439219 we have obtained here, and the Heun's value was 16.3197819, 9.94. 3 and 4, 33.6771718, 37.1992489, 10.46, 75.338962, 83.3377674, 10.62. I think you will have to check it of your own whether this satisfies this or not. I hope there should be no mistake here. So you will be calculating all the steps and compare it with this result. So now we will be going back to the slide again. So the one improvement we have seen. The next improvement we'll be watching here is the midpoint method. Similar to Heun's method, but it predicts the slope at the midpoint of an interval rather than at the end. In the predictor corrector approach or Heun's method, what we have done, we have taken this point slope and this point slope and made average of these two and predicted that slope predicted the point using that slope from here. But now I will be determining the slope at the midpoint of these two, starting of the interval and the finishing point. Will be taking the middle point, and I will be going to the middle point and getting the slope of that middle point, and this slope will be applied in this point to get the next point here. So this is the improvement in midpoint method. So the previous was taking two boundary points slope and made average, and the midpoint method says only take the midpoint slope and apply it in the initial point to predict this one. So as you can see here, so the slope in the incremental function, as incremental function what we have seen in the Euler case, that will be replaced by the slope of the midpoint of the interval. That is the only difference. So that's why whenever we'll be calculating firstly this point we'll have to evaluate. If we want to take the slope of this point, first we have to go to this predicted point using Euler's method. So first we'll be going to this point using Euler method, so the step size will be half in the first case, as we are going to this point using Euler method. So if it is h, we will be using h by 2 to get to this point, and then that's why h by 2 has been used here, as you can see. And this is yi plus half, as you can see here. So this point, once we obtain this point, then we'll be taking the slope at this point. As we know, x or ti plus half we know, and we'll be knowing this value, and using this ti plus half and yi plus half, we will be calculating the slope at this point, and this slope will be used here in this initial point. The Euler method will be similar. The only difference is the midpoint slope will be used here instead of the slope at initial point. That is the difference in midpoint method. So very easy, I think you can understand. Now I will be working out a problem here. So the problem, I will be copying this to our script. Copy this thing here. So this is the question. Now we'll be using midpoint method here, and before going to the method of midpoint, first we'll have to solve it analytically. As you know, this should be solved analytically, and this one, as you can see, this is also a separable variable. We can write, first we are going for the analytical solution. dy by dx equals to y x square minus 1.2. We can write dy by y equals to x square minus 1.2 dx. So if we integrate it, both sides, we will be getting ln y equals to x cubed by 3 here minus 1.2 x plus c will be getting the initial value is given y naught equals to 1, so we can use it here. Ln 1 equals to, this will be 0 0 plus c only, so ln 1 equals to c and c will be equals to 0. That's why you can write the analytical solution as ln y equals to x cubed by 3 minus 1.2x, from which we can write y equals to e to the power x cubed by 3 minus 1.2x. This is the analytic solution in our case. So analytic solution we have obtained here. Now I will be going to the midpoint method, our main focus in this math. Function of xy in our case here is yx square minus 1.2y dy by dx. So we need to calculate, we know that y0 equals to 1, and now we need to calculate the slope at midpoint. So for getting slope at midpoint, I need to go first at the midpoint. So as we'll have to use step size of here given, if you see the question, the step size is 0.25. So h is 0.25. Instead of going 0.25, I will be going half of that, that is 0.125 I will be going. So instead of going this point from 0 to 0.25, I will be rather going to 0.125 using this slope. Slope at this point should be calculated as 0, 1, as y0 equals to 1. So first of all, this slope is required, so that if I want to calculate point y at 0.125, this 125, if I want to calculate using y naught plus f0 comma 1, we'll have to calculate, and the step size will be halved here, so 0.125 will be used. So this one should be calculated. So f0 comma 1 will be using this 0 and 1 will be putting this value in this equation, and this will give you minus 1.2, and this minus 1.2 will be putting these values here. So y01 plus minus 1.2 multiplied by 0.125, that is the slope of the midpoint, and which will be 0.85. Now we'll be using this midpoint slope for predicting original y midpoint method for 0.25, the next step from 0 to 0.25. So 0.25 will be using 0 plus the slope at midpoint, that is the slope at midpoint we should also calculate. We haven't calculated it yet, so using this point we'll have to calculate the slope, that is slope at midpoint means f of 0.125 comma 0.85, which will be equals to that is this point slope. That means this slope we'll have to calculate 0.125, and y value we have obtained as 0.85. Here 0.85 we have obtained. So put this value in this equation to get this one. It will become minus 1.00672. Put this value here, minus 1.00672. So I am using slope of midpoint in the Euler method instead of the initial point slope. That is the correction, multiplied by h, that is 0.25. In this case I am using original h. While determining the midpoint, then we had used this one, half of the h, but now I am usual h will be used here. So this one is 1 minus 1.00672 multiplied by 0.25, and this will give us the answer as 0.74832. Whereas the true solution, if we go true solution at 0.25, as the analytical solution is known, the analytic solution, this one. So if we put the value of x equals to 0.25, this will give us 0.744686. So now you can calculate the true error here, true value minus predicted value at midpoint divided by true value into 100%, which will be equals to 0.488%. You see, this is very close to the original solution, only 0.488% of error. So this modification are converging. Now I am going to the step 2. If that was step 1, now I am going to step 2. If it was step 1. Our question says interval from x0 to x2. So I will have to go from 0, 0.25, 0.5, 0.75, then 1, 1.25, 1.5, 1.75, then 2. So I will not be going for all this. You have to try this, and neither I will be doing here all of these steps, nor I will be giving this in your exam. I might give 1, 2, 3, up to 3 steps, I hope, in your exam. But you'll have to practice all these things in your home. Step 2 now will be, we know that y.25 is, obviously we'll be using midpoint method. We'll be focusing on global error here as well. I know what you know what to do for the local error, so I am not going for that. So ym.25 is 0.74832, and f of 0.25 should be calculated, 0.74832. This one we haven't calculated yet. So from the analytic solution, now this is the initial point, using which we'll have to calculate 0.5, the next point. But before that, we need to calculate the value of midpoint to get the value of midpoint slope. So for that, we need this initial point slope. For this step, this is the initial point's slope, and that's why we can obtain it from this formula, this particular equation. We can put the values of x and y, and we'll be getting the value as minus 0.851214. using this value, I'll be predicting now the midpoint value. In between these two, the midpoint value will be, as you all know, the midpoint value will be 0.375. That is 0.25 plus 0.5 by 2. Sorry, 0.25 by 2. The increment, half of the increment, that will give you interval, that will give you the midpoint. This midpoint value we can use Euler method to determine this value. Obviously you will be using midpoint value of 0.25 plus the slope, this one, slope at this point, that is 0.851214 multiplied by h by 2 in this case, so 0.125, half of the step size, as we are determining the midpoint. This value is this one, so the value at midpoint will be 0.64192. And the function here, now the slope will be getting 0.375 comma 0.64192 from the equation, this equation, x and y value. If we put the values, we will be getting the value as, the slope will be 0.68034, and this is the slope of the midpoint, which will be applying it over the initial point to get the midpoint value of 0.5 accordingly. So we'll be using here 0.25 plus, instead of using the slope at 0.25, we'll be using slope at this point, this one. So this will be 0.375 comma 0.64192 multiplied by h, that is 0.25. .74832 minus 0.680034 multiplied by 0.25, which will be equals to 0.57832312. The true value we can also calculate using the analytic solution, what we have found here. Put the value of x 0.5, then we'll be getting the value as 0.57216. Look, it is very close to the midpoint assumption is very close to the true solution again. So if you calculate 80% here again, you'll be getting 1.075%. So similarly, you'll be getting all the values as I am drawing here, a chart, a table. X, Y true, Y midpoint, and epsilon t percentage. Zero, 1, 1 at the beginning. For 0.25, it becomes 0.7 0.44686, it becomes 0.74832, and the error was 0.488%. For 0.5 we obtained 0.57216, it was 578312, and this is 1.075. It is 0.75 now, 0.46796, 0.47519, 1.545, 1.42035, 0.4277, 1.7485, 1.25, 0.42786, 4.434541, 1.5615, 1.5, 0.50916, 0.512967, 0.7477, 1.75, 0.73085, 0.721963, 1.216, and finally for 2 we'll be getting 1.30561, 1.237216, 5.2385. So this is our result. This is our result, what we'll be getting using midpoint method. So you'll be performing this of your own. Now one concept I will be just giving overview, which will not be focusing further. I'm just going for the theory rather than going to the mathematical problem, is the Ranga Kutta method I'm now discussing. This method can achieve the accuracy of a Taylor series approach without requiring the calculation of higher derivatives. That is, in Taylor series we have seen there was an expansion might be up to infinite terms, which if we use we might get the accurate higher accuracy, but the similar accuracy might be obtained without using or requiring calculation of higher derivatives. In Taylor series we have seen we needed the higher order terms like f prime x by 2 factorial h square or f double prime, so dot dot dot. So these things we have seen in case of Taylor series that we need higher derivative terms, but this method says you will not have to use any higher derivative to get to the solution. And the increment function in this case, the increment function in predictor corrector approach we have seen the average of two slopes. In midpoint method we have seen the midpoint instead of the initial point, And this Ranga-Kutta method says the increment function will be of this like structure, where k1, k2, k3 all are given with some formats, where k1 is the very initial point slope and all others will be the slope at different points, which we'll be getting based on which order of Ranga-Kutta method we'll be using. Among all the orders of Ranga-Kutta methods, the most popular one is the fourth order Ranga-Kutta method, where we will have four orders, k1, k2, k4, k3, k4s are 4 points where we'll need to take slopes. In this figure, this is explained here. We have taken slope at 4 points, and we have taken given some weightage to these 4 points, and similar to the trapezoidal rule, if you can remember, we have used this one. Similar like trapezoidal rule, we can say we have used here, that we have given weightage 2 times to this k2 and k3 and 1 weightage to k1 and k4 each, and these 6 factors are 6 times things are divided by 6 to multiply by h, and this terminology, this incremental function is assumed to be giving the most accurate prediction, which will be giving you the most closest, almost the closest close value to the true solution we can expect. Previously we have either taken midpoint slope or we have taken 2 slopes average, but in this case we are taking this incremental function. At 4 points we will be getting the slopes. Where will be these 4 points? First is the initial point, as you know, and k4 is the final point slope, as we all know, and 2 more additional points are there. As you can see, these points are ti plus half h plus yi plus half k1h. That is, based on this k1 we'll be taking another point at that k1h, and when this is the midpoint we are going, but we will be taking y as different points. We will be taking y as we will be taking x at same point, but we will be taking y of different values to get the slope. That is, this one is y1 plus half k1, and this for k3 we have used y1 plus half k2 of h. These 2 y values will be differing, and it is experimentally seen that if you use these values you will be getting all these 4 values. If you take this in this manner, you will be getting most popularly used method, the most almost close to the original solution we'll be getting. So this is the procedure. I hope you'll be able to understand, but I will not be performing any math, and hopefully I will not be giving probably in your exam as well, but I think you should learn it of your own, which might be used in different purpose for different cases, just because it is giving you very higher accuracy than any other method you can even expect. Anyway, there is a problem. You can practice of your own for your convenience, but I am declaring that I will not be giving any question regarding this in your exam. Okay, now I am giving a gist before finishing our lecture today. This is the performance of different methods are given with different legends, as you can see here. The true solution, the analytical, that is the true solution, is given with totally black curve, and the Euler method is the most worst case. If I say Euler is the worst case where we will be predicting, but based on this Euler all modifications are done. That's why you cannot neglect or this Euler method. Based on this one, all modifications are done. And if you see all other methods, Heun's method, midpoint, and another Wellstone method is there, what we haven't discussed, and other Butcher method, Ranga Kutta fourth method I have discussed, but not given any mathematical explanation or problem I haven't worked out. But all the methods are there. There is a comparative analysis in the graphical sketch, as you can see, and the percent relative errors are also given there, where we see that Butcher method is likely to be the most efficient here, although RK method is also efficient even from the Heun's method or midpoint method. Anyway, so this was the lecture for week 5. So hopefully we'll be finishing it our course content in the lecture next lecture, that is for the week 6. So thank you everyone for joining and being with us.